Okay, let us continue the third part of today's class. Okay. So in this example, 1 over rho lambda I is equal to 4 and 5 are greater than mu. Okay, we can see that, okay, when I is equal to 4 and 5, 1 over rho lambda 4 is here, and 1 over rho lambda 5 is here. Okay, they are both greater than mu, okay, which is here. Okay, so PR minus P plus 1 OPT is equal to P5 OPT. Okay, because R is equal to 5 and P is equal to 1. So it is equal to P5 OPT, which is smaller than 0. Okay. Therefore, according to the algorithm, the power associated with eigenchannel 5 should be set to 0 and P incremented to 2. Okay. Okay, we have taught this slide. Okay, so in this figure, figure 3.3 part B, we can see that eigenchannel 5 is discarded. Okay, generally, but not always, mu increases each time P is incremented, which is what we have assumed in this example. Okay, you can see that, okay, when P is equal to 1, the value of mu is here. And when P is equal to 2, the value of mu is here. So mu increases. Under that assumption, okay, the values of Pi increase accordingly. Okay, what is the meaning of accordingly? Let us see the handout. Okay, page 86, problem 1. What is accordingly? Okay, solution: in a way that is suitable or right for the situation. Okay, let us go back to the slides. But despite that, 1 over rho lambda 4 is greater than mu. Okay, let us see again. Okay, 1 over rho lambda 4 here is greater than mu. Okay, here. Okay, so P4 OPT is smaller than 0 in this example. According to the algorithm, P4 OPT is set to 0 and P is incremented again. Part C shows the situation after repeating steps 1 and 2 when P is equal to 3. Okay, let us go to part C. Okay, this. So in this figure, we can see that we discard these two eigenchannels. Okay. And modes 1, 2, 3 are used modes. Okay. So in this case, mu has increased sufficiently that PR minus P plus 1 OPT is equal to P3 OPT. Okay, because R is equal to 5, P is equal to 3. And 5 minus 3 plus 1 is equal to 3. And P3 OPT is greater than 0. Okay, we can see that P3 OPT is greater than 0. At this point, all the eigenchannel powers have been assigned non-negative values, so the algorithm is complete. complete. Excuse me. Okay. So this algorithm works because it accomplishes its goal of finding the set of PIOPT that A sum to 1 and B result in the maximum capacity. Okay, because this point is hard to understand, so I changed the color of this point to gray, and you can ignore this point here. The reason that the capacity is maximized is because the algorithm finds the maximum number of non-zero eigenchannel power levels consistent with the constraint. Okay, the constraint means that this constraint. Okay, let me show you. Okay, the constraint is summation I is equal to 1 to R. Pi is equal to 1. Okay, excuse me. Okay, since the number of non-zero power levels is maximized, the number of non-zero terms in equation 3.35. Okay, let us go to equation 3.35. Okay, in equation 3.35, COPT is equal to summation I is equal to 1 to R, where R is the channel rank, and log 2 of 1 plus rho, where rho is the SNR at the receiver, times PIOPT, where PIOPT is the optimal power of the ith eigenchannel, and times lambda I, okay, where lambda I is the ith largest eigenvalue of the matrix H times H Hermitian. Okay, let us go back to the previous slide. Okay, so equation 3.35 is maximized, which in turn maximizes the capacity. By examining figure 3.3, okay, let us go to figure 3.3. Okay, excuse me. Okay, this figure, this is part A, and this is part B. Okay, and this is part C. Okay, we can also learn something about how the water filling algorithm depends on the signal to noise ratio. First, consider the limiting case when rho approaches infinity. Under that assumption, regardless of the value of P, the values of the terms 1 over rho lambda I approaches 0, which means that the gray areas in the figure shrink. Okay, let us go to the figure again. Okay, we can see that when a rho approaches infinity, then 1 over rho lambda I approaches 0. So this approaches 0. Okay, this approaches 0. This approaches 0. This approaches 0. And this also approaches 0. So the gray rectangular shrink, okay, and disappear. Okay, excuse me. And all of the eigenchannel power levels approach the same value. Okay, why? Let us go back to figure 3.3 again. Okay, so because this and this are all approach 0, so P1 OPT is equal to mu, okay, and P2 OPT is equal to mu, and so on. P3 OPT, P4 OPT, and P5 OPT all equal to mu. Okay. At the opposite extreme, when rho approaches 0, the values of the 1 over rho lambda I terms become large, which means that the values of PIOPT become negative. Okay, because PIOPT is equal to mu minus 1 over rho lambda I, and because mu is a positive constant, okay, so PIOPT become negative, resulting in the need to discard the eigenchannel powers. Okay, however, since the sum of the eigenchannel power levels must equal to 1, or must equal 1, it is necessary to retain. Okay, what is retain? Let us see the handout. Okay, page 92, problem 1. What is retain? Solution: to keep or continue to have something. Okay, let us go back to the slides. Okay, retain at least one of the PIOPT terms. Okay, in the limit when the signal to noise ratio becomes small, only P1 OPT is retained. Thus, in the small rho limit, the water filling algorithm tells the transmitter to place all its power in the eigenmode with the largest eigenvalue. Table 3.2 summarizes these observations. Okay, let us go to table 3.2. Okay, table 3.2 is the summary of water filling algorithm dependence on signal to noise ratio. Okay, when the signal to noise ratio rho approaches 0, the water filling performance places all power in eigenmode with the largest eigenvalue. When the signal to noise ratio rho approaches infinity, the water filling performance applies equal power to all eigenmodes. Okay, next let us go to section 3.6, single mode eigenbeamforming. Okay, single mode eigenbeamforming refers to the particular form of eigenbeamforming in which information is only transmitted over a single eigenmode, the one with the largest eigenvalue. As we have discussed, this approach is equivalent to 4 eigenbeamforming when the signal to noise ratio is low. In single mode eigenbeamforming, S tilde is equal to S tilde 1, and the remaining terms are zeros. Okay, let me ask you a question. Do you know how many zeros are there in these vectors? Okay, the answer is r minus 1. where R is the channel rank. Okay, so S tilde is equal to S tilde 1 and R minus 1 zeros transpose, since only the first eigenmode is used to transmit symbols. Okay, after pre-multiplying by V, the transmitted data vector is given by S is equal to V times S tilde. And we write each element of V here. Okay, please note that V is an NT by R matrix. Okay, why? Let us go back to the first time where V appears. Okay, search for matrix V. Okay, we must be getting close. Okay, here. Okay, H is equal to UdV Hermitian, and the dimension of V Hermitian is R by NT. So the dimension of V is NT by R. Okay, let us go back to the slide. Okay, excuse me. So the elements of the matrix V can be written as V11 to V1R, and V21 to V2R, and so on. And the last rows are last row is VNT1 to VNTR. And the vector S tilde is equal to S tilde 1, and the remaining terms are zeros. Okay, and after multiplying V and S tilde, okay, this matrix and this vector together, okay, we can get this vector. The first term, the first element of this vector is V11 times S tilde 1. Okay, that is this term and this term. And the second element of this vector is V21 times S tilde 1. So V21 S tilde 1, and so on. And the last element of this vector is equal to VNT1 times S tilde 1. Okay, so it is equal to VNT1 S tilde 1. Okay, this equation shows that even though there is only one eigenmode being used to transmit data, signals are transmitted on all NT transmit antennas. Okay, we can see that, okay, on the first transmit antennas, the transmitted signal is V11 S tilde 1. And on the second transmit antenna, the transmitted signal is V21 S tilde 1, and so on. And on the last transmit antenna, the transmitted signal is VNT1 S tilde 1. Okay. In particular, the transmit antennas are fed with scaled versions of the single data symbol being transmitted. Okay, you can see that on the first transmit antenna, okay, it is fed S tilde 1 times the scalar V11. Okay, where S tilde 1 is the single data symbol. And on the second transmit antenna, it is fed the scalar V21 times S tilde 1, okay, the single data symbol, and so on. And on the last transmit antenna, it is fed VNT1, okay, which is a scalar, times S tilde 1, okay, which is the single data symbol. Okay, in this sense, single-mode eigenbeam-forming is similar to conventional beamforming, which applies complex weights to each antenna element in an array. In conventional beamforming, the weights are chosen to point the beam in a desired physical direction. However, in single-mode eigenbeamforming, the weights are chosen to match the channel matrix. Okay, what is the meaning of this sentence? The weights are chosen to match the channel matrix. Okay, let us see. Go to slide. Okay, page 98. Okay, because the weightings are V11, V21 to VNT1, which are the elements in the matrix V. And what is V? Okay, let us go to the first time that V appears. Okay, first time of V. Okay, first time. Okay, here. So H is equal to U times D times V Hermitian. Okay, so we can know that V comes from H. Okay, let us go back to the single mode eigenbeamforming. Okay, single mode eigenbeamforming. Okay, because these weights comes from matrix V, and the matrix V comes from the channel matrix H, so we say that okay, excuse me. Okay, so we say that the weights are chosen to match the channel matrix. Single-mode eigenbeamforming is a more abstract concept and can be thought of as a generalization of conventional beamforming. One might ask, what benefit is there in only transmitting data using one eigenmode? Okay, the answer is that it enables higher throughput than can be achieved with a SISO system at the same signal-to-noise ratio. Okay, to see this, consider the following expression for the capacity of a MIMO system that uses single-mode eigenbeamforming. Okay. C single mode is equal to log 2 of 1 plus rho 1. Okay, where rho 1 is the received SNR on the first eigenchannel, and it is equal to log 2 of 1 plus rho, okay, which is the SNR at the receiver, times P1, which is the power of the first symbol to be transmitted, and times lambda 1, okay, which is the largest eigenvalue of the matrix H times H Hermitian, which follows from equation 3.27. Okay, let us go to equation 3.27. Okay, in equation 3.27, okay, excuse me. CEIG, okay, that is the capacity with eigenbeamforming is given by summation I is equal to 1 to R log 2 1 plus rho times the expectation of the square of the absolute value of S tilde Okay, it is 25 minutes. See you next time. Goodbye.